Welcome to the presentation about fast, simple and accurate image derivatives. My name is Anders Hast, and this presentation is based on a paper with a very long title that I published some years ago. And it's about computing image derivatives. Why would you use them? Well, they are used a little bit everywhere in image processing and computer vision and so on. For instance, for key point computations, like the Harris corner detector, or the determinant of Hessian, and so on. For image gradients, used in visualizations, for edge detection, image editing, special effects. There are many applications for image derivatives. So what would you do? You would probably use the Sobel filter, which is quick and it's dirty. It does its job, but not in a very good way. Why not use the Farid-Simoncelli filters instead, which are kind of optimal, or the Hast filters, which I designed, which are more flexible. The cost is not much more, but the result is much better. Sobel filters are separable. That means that you can use one kernel for averaging and one kernel for differentiating, which will give you a derivative which is computed in a surrounding of each pixel. Since I come from the computer graphics area, I know very well this equation, which you will find in most computer graphics textbooks. It says that you can design a patch, a spline patch over certain points, as in the image. And I was thinking, okay, why not do that over pixels instead? And what you need is a spline basis, some kind of spline that are useful for this purpose, and then the surrounding, the pixels in the image. And then I was very happy when I could derive this equation, which shows that you can separate the spline into two kernels, which are then convolved with the image. So these are the two kernels, and that G in this case is the image. And cubic splines are used in many cases because they don't bend too little or too much. So these are defined by 4 elements, but in image filtering we want an odd number. And the solution to this, which is shown in the image, and please read the paper for a better explanation than I will do now, but by filtering twice, you get the correct result. And that actually means that you can filter the image by convolving the kernels first and then convolving with the image. This will give you a 7-element long kernel. And in this case, one is for differentiation and one is for interpolation, just like in the Sobel case. And the nice thing about cubic splines is that they can mathematically be differentiated as shown in these formulas. And you can see that some parts here are actually the kernels that you need. And the kernels are evaluated around the center. That means that the U and V values that you use for defining the splines are set in this way as shown here. Now, this has been a lot of math very fast, but let's look at a real example in Matlab code. First, we'll need a spline, and I chose here the very nice Catmull-Rom spline, which is defined like this. So here we have the base matrix. And then you need to set the center values for U, which is the spline itself, and UP is then the derivative. And then you compute the kernels simply by multiplying these vectors with the basis matrix. And then you just convolve. That's all. And note here that we actually convolve the kernels, K and D, to get the 7-element long kernel. So this means that you can use any spline you like for each of the 4 kernels. So you can mix. You can take B-splines, Bezier splines, if you want to sort of low-pass filter the image, and it works for the second order derivative as well. So please have a look at, you can find more information in this Wikipedia page or in my original publication. Thank you for listening.